Okay, let's look at reversible reactions. In our early years of studying chemistry, we're always told to write a chemical reaction in a certain way. So we have reactants on the left-hand side, A and B, we have an arrow denoting the direction of the reaction, and we have products on the right-hand side. As an example, if we burn paper in the presence of oxygen, we get carbon dioxide and water. And we're told that this reaction goes to completion. In other words, 100% of the reactants are used and converted to our products. Now, it is possible to get the reverse of this reaction, but to set this reaction up in reverse is very, very difficult. So we don't readily form paper and oxygen from carbon dioxide and water. We've also got a second set of reactions that, given the right set of circumstances, we can reverse them. So if we have our A plus B giving us C plus D, if we add heat or we increase pressure, we often find that we can convert our product back to our reactant. So as an example, if we combine hydrogen gas and oxygen gas, we put it in the presence of a spark, we create water quite readily. Now we can also use electrolysis to split this water to get our oxygen gas and our hydrogen gas. So we can reverse this reaction reasonably quickly. Now there's a third set of reactions that at any given set of conditions, upon completion, will still contain reactants and products. And these reactions are known as reversible reactions. So a reversible reaction is one in which we observe significant concentrations of reactants and product at that point of completion. Let's look at an example. Let's say we combine hydrogen and iodine to give us hydrogen iodide. To start with, in this first graph, we're going to start with 100% in the reactant form and nothing in the product form. And what we observe over time with a reversible reaction is that, yes, the concentration of our reactants will decrease, but you'll notice that it doesn't go to zero in one of the completion reactions that we talked about before. Our product, as we'd expect, will increase over time, but it will also never reach 100%. Now, the interesting thing about reversible reactions is that we can start from the right-hand side and we get a similar scenario. So if we started with all hydrogen iodide and we put this and we observed what happened, we'd find that over time our product concentration would decrease, but once again it wouldn't go to 0%. And our reactant, in other words our hydrogen iodine, would increase in concentration, but once again wouldn't go to 100% either. So this is telling us that at the completion of the reaction, we're getting significant concentrations of both reactant and product. Now the other interesting thing about this is that we can actually plot the rate of the reaction as the reaction proceeds. So our red line here, we go back to this graph, is actually measuring the rate of reaction of our reactants, or what we call the forward reaction. And as we'd expect, our rate of reaction will decrease over time. Now it doesn't become absolutely zero, instead it gets this consistent rate of reaction over time after a given period of time. Now our rate of reaction for our product going to reactant obviously increases over time, but once again it levels out. And it's no coincidence that both the rates are actually equal after a certain given period of time. Let's look at what we could conclude from this. At completion, the concentration of reactant and product are constant, regardless of which direction we started. And secondly, at completion, the rate of reaction forward, this one, will equal the rate of reaction in reverse. So what do we conclude from these observations? First of all, on a macroscopic level, we can see that after a given period of time, there's no change in the concentration of reactant or product. And secondly, on a microscopic level, we're getting a continuous change. That's what's indicated by our rate of reaction. This reaction forward is still occurring, but the rate of reaction backwards is equal to our rate of reaction forward. And that's why we get no net change in concentration of our reactant or product. So at chemical equilibrium, our rate of reaction forward will always be equal to our rate of reaction in reverse, and that's what gives us a consistent and constant concentration of reactant and product.